All right, we have started. So the title of this thing is called Real Numbers. There's a little symbol that they use. I don't know if you've seen this. I doubt in Algebra 1 they did this. But they use a R, but it's kind of a weird looking R. This is how I do the real number thing. Put a capital R and then make that straight line like a double straight line. That little symbol, that's close enough. If you look in the book, you can kind of see it's a little more fancy looking in the book. But that's kind of how I do real numbers. Usually I would go 2 lines and then like that. That's how I would usually draw it. Whoops. Okay. So that is a symbol for real numbers. I don't even care if you put the little double thing right there. If you just put a big old capital R, that represents real numbers. Now, basically, every number that you've learned up to this point have been real numbers. I really doubt that you did imaginary numbers in Algebra 1. All right, it's usually not an Algebra 1 topic, but there are things called, have you ever heard of it before? You ever heard of imaginary numbers? They're not numbers that you just make up that are floating around. You have heard of imaginary numbers? Yeah, so it's, for instance, I'll just give you a quick instance, because we're talking about reals, we're not talking about imaginaries, so I don't want to get into this too much. But what if I did this? What if I said the square root of, what's the square root of 1? What does that mean, the square root? You guys are scaring me. You're in Honors Algebra 2. It's 1, right, because what number times itself is 1? 1 is, not 0. You just said it. You just said 1. You had it right the first time. All right? Everybody with me? What is this? What's the square root of 9? 3. What's the square root of, 81? 9. What's the square root of -1? That's right. It doesn't exist, does it? Not in the real numbers, it doesn't exist. But it does exist in the what? Imaginary numbers. Okay, there's a whole class in college that I took, and it dealt with imaginary numbers. It was called complex analysis. Could you even imagine taking a class called complex anything? Just sounds horrible, doesn't it? Just the word complex. But it basically was like algebra and calculus, all with imaginary numbers instead of real numbers. But that's not what we're talking about. Okay, I kind of got off track with this stuff. We are going to deal with real numbers because a lot of people think, well, every number is a real number. But no, that's not technically true. Oops. Let me just get rid of these things. Get rid of this, get rid of this. All right, we don't want to see those anymore. So we are going to deal with real numbers. There are some subsets of real numbers, okay? So there are things called rational numbers. Rational numbers. And there's something that's the opposite of rational numbers. Hunter, you're going to sit up front in about 2 seconds. I know he does, but you still keep turning around. All right? I'm not going to deal with this. This is supposed to be honors class. I don't deal with this stuff in honors class. Thank you. All right, so rational numbers. What would be like the other end, the opposite of rational numbers? Irrational numbers. Good, you've heard that before. Do you want us to write this down? Absolutely. If I write it up here, you write it down. I don't understand why people ask me that question. I get that question every single year. But yes, if I write it up here, you should be writing it down. All right, so you got rational numbers, you got irrational numbers. So let's talk about, basically, a rational number is any number that you could make into a fraction. Any number. What about the number 4? Is that a rational number? Sure, because I can make it into a fraction, right? I could go 4 over 1. I could go, what? 12 over 3. I could go 16 over 4. Would you agree? So these are rational numbers. Irrational numbers, and a rational number, the decimal, like 2/3. Is that a rational number?
Well, yeah, it's a fraction.
It's a fraction, that's right. Okay, because look at the word rational. It's got the word what in it? Ratio. What's a ratio? It's a fraction. That's how you can remember it, okay? Ratio is a fraction, so any fraction is a rational number. The rational numbers, let's just take 2/3. 2/3 is what? Do you know what it is off the top of your head? It's not It's not 3. That's 1/3. 0.6, right? 6, 6, 6, and then repeating. Or some people just end it right with the 7. But does it really end there with the 7? No. It repeats. It keeps on going. It doesn't stop at 7. It doesn't like automatically a 7 pops up. We just round it to 7. Everybody, you've done that before, right? But this repeats, and it keeps on repeating. You can just put 0.6 repeating. A rational number either does one or two things. It either stops, right? Like 12 over 3. That's a 4. It stops at 4, doesn't it? There's no decimals. 2/3, it just repeats. It starts with a number and just repeats. Some other decimals or some other fractions stop at certain decimal, like 1/8. I think 1/8 is 0.125, and it stops right there at 5. It doesn't repeat. Those are all rational numbers, okay? It either repeats. Some weird fractions, I can't think of anything off the top of my head, but some weird fractions, it might have 2 or 3 numbers and just keep repeating those 2 or 3 numbers all the time. That indicates that it's a rational number. An irrational number does not repeat, and it doesn't stop, okay? It just keeps going with just a whole bunch of random numbers. For instance, what's probably the most famous irrational number that you've probably used? Pi. Pi is an irrational number because pi is not equal to, what should we always write? Approximately equal to what? 3.14. Now you could keep going, right? You could Google it. You could Google what is pi up to 1,000 decimal places, and they'll tell you, right? They'll show it to you. You could take it up to 1,000,000 decimal places. You could keep going forever and ever, because now I only have it memorized up to 159. Okay, 3.14159, that's it, because there's really no reason to memorize it any further than that, because you just don't have the equipment to measure things that accurately anyway. But you just put it right there. Thank you. So we put a little ... What does that mean? It means it keeps on going. Do you see any pattern here? It doesn't develop any pattern. It doesn't repeat anything. Now, if you stretched it out, there's a couple places where it repeats like a 7 or a 2. I forget exactly what numbers. Every once in a while, you might have 2 7s next to each other. But then after that, it goes random again. All right? So there might be a couple places where it repeats, but it doesn't repeat the same pattern over and over again. Anytime you have that, that's considered a what? Irrational number. If you took the square root, we did square root, right? What's the square root of 9? 3. So is the square root of 9 a rational number or an irrational number? It's rational because it stops. It simplifies to be 3 and it stops right there. So that's a rational number. An irrational number won't. So what if I had this, the square root of 3? I don't know what that is. Let me look it up. Is it 1? 1 times 1 is 3?
It's 1.5.
Is it 1.5? It's not. It's 1.73. I'm just writing off from my calculator. 0, 5, 0, 8, 0, 8. So that's all that my calculator takes it out to. All right. But does it stop right there just because my calculator stops? No, it doesn't. It does what? Keeps going. Now, it almost looks like it is a pattern, right? 0808, and you might think, oh, it keeps that pattern. But if I Googled it and I went on there, if I had a calculator that went out a lot more decimal places, it would not keep repeating the same pattern, all right? So this is an irrational number. Like the cube root of something that doesn't come out even, like, I don't know, the cube root of 11. I wrote that in my notes. It's a weird number. I don't know what it is. I'm not even going to put it in, but that's an irrational number. Everybody got that? So you got rational, you got irrational. That's the end of the irrationals. We're not going to talk any more about irrationals. All the other ones, and they're still a real number. Even though it doesn't repeat a pattern, it's still a real number. All these numbers, probably every number that you've ever dealt with up to this point were always real numbers, okay? But then they have subsets of real numbers. So let's talk about those. And you've probably talked about these even before you started taking Algebra 1 or pre-algebra or anything else, okay? The next one underneath rational numbers is called an integer. You've heard of integers, correct? And we have a letter that represents integers. I'll just put it in a parentheses right there, and it's a big old Z. And again, they usually put it like a double bar there just to make it look a little different than a regular Z. If it was me, I would just put a Z, all right? I don't care about making it super fancy. Just put a Z, that's good enough. These are integers. What in the world is an integer? Well, what about 2/3? Is that an integer? No, it's a real number. It's a rational number, but it's not an integer. Integers are basically whole numbers and negative whole numbers. I hate to say that because a whole number is not a negative number, but as far as us just understanding it, it's like negative numbers, 0, and whole numbers. Well, 0 is a whole number. So it starts with 0. What's the next integer to the right of 0? It's 1, because they don't come out to fractions. They're all just that number 0.00000, okay? So 1, 2, 3, and just keeps on going. Is that it, though? Is it just at 0? Nope. There are also negative numbers as well. So it would go -1, -2, -3, what? ... because it keeps on going forever and ever. So these are the set of integers. They're not in between, no in-between numbers, no fractions. Well, I guess you could look at it as a fraction, like 4/2. What's 4/2? It's 2. 4/2 is a fraction, but it reduces to an integer. Everybody got that? Yeah, pretty simple. But they're going to refer to that a lot, because if they're going to talk about integers later on in the book, they might as well talk about what an integer is right at the beginning. Would you agree? Right? We got to have some definitions first before we actually start working with them. So that's integers. Let's do a whole number. Whole numbers. And they use a letter for this, and it's nice. I don't know why they use Z for integers, but probably because if they used I, that would indicate, what do you think? I. We talked about it, and we said we're not really going to use them, at least in this. Imaginary numbers, right, imaginary numbers. But what do you think, what letter do you think? W. Very good. All right, and they might make it a little fancy. If you look in the book, it's kind of curvy and a little thicker at some part. It just looks a little different than your regular W, but that's okay. We'll just use W. So what are all the whole numbers? I had a teacher a long time ago, probably in high school or middle school or something like that. They always said the way to remember the first number of a whole number is, what is a whole? It's nothing. It's 0, right? Right? If you dig out a hole, there's nothing there. So that's what it starts with. The whole number starts with 0. So it starts with 0, and then it goes to the right. They're basically positive integers including 0. All right? So 1, 2, 3, and it keeps on going following that pattern, ... Those are your whole numbers. And then you got your natural numbers, or some people call them, I'll put a or, sometimes they call them counting numbers. Oops, I got 2 I's there, I don't know why. But anyway, you get the idea. I'll make that big old thick I. Counting numbers. So if I took a whole bunch of stuff and I throw it on the floor and I asked you, count them up, what number would you start with? 1, okay? So that's counting numbers. So counting numbers start with what? 1. So they're just like whole numbers except for one difference. What's the only difference? Doesn't have the 0, that's right. So if I'm going to count something, I'm going to start with 1. I don't look at that and say, oh, 0, 1, 2. I never do that, do you? All right, so I start with 1, same thing. So those are counting numbers. Oh, by the way, they use the letter N. And again, it's a big fancy capital N, but they use the N for counting numbers. All right. Yeah, that's good enough. I put a note on there, but I've already talked about that. All right, here's, like, how in the world could they ask questions about this? Well, here we go. This is example 1, our first example. So example 1. Here's the question. I'm not going to write it down. I'll just read it off to you. If you have your book, you can see it. Example 1, it says, state the most specific subset. All these are subsets. What are they? Natural numbers, there's a subset. Whole numbers, integers, rational numbers, they're all subsets, okay, of a real number. Everybody got that? So which one of these, rational, integer, whole, counting, is what they ask for? So part A, it gives you -2. I'll just write them out. Part B is 7/11. C is 2.3 repeating. And then D is the square root of 3. All right, we kind of talked about these. So it says, what's the most specific subset, all right, of -2? -2, what's the most specific out of all the ones we talked about would -2 fall into, Angela? The integers, that's right, it's an integer. It's not a natural number, it's not a counting number, or it's not a whole number because you don't have any negatives, okay? The only negative numbers that aren't fractions, I guess you could call, are integers. So you could do it like this. This is how they write the answer. They write it kind of fancy, but they write this, that -2 is a subset. I don't know how long ago it was for you where you learned sets and subsets. You remember ever learning that stuff? Maybe middle school? You never learned that? It used to be a big thing a while back. Maybe they're not doing it so much, but this is how they do a subset, or as an element of. That's what this is. It's kind of like a C with a line in. Kind of looks like an E, but a little bit of a weirder looking E. That means is an element of. So -2 is an element of what subset? All the integers. And what letter? What fancy letter do we use for integers? Right, we use the big old Z right there. So that's how the book writes the answer. Okay, I would be fine if you just said what? What is -2? It's an integer. All right. To me, I probably would rather you say that. But this is what the book says. So when you look at the book, you're like, what in the world is that thing? I've never seen that before. That's what they mean. -2 is an element of the set of integers. That's technically how you would say that. But I don't think they teach sets and all that kind of stuff like they used to. It used to be like, I don't know, you ever hear people talk about the new math? Like back in the 70s and 80s, they talk about the new math, and it was all like sets and subsets. And so I was a little bit a part of that, right, when I was a kid learning that. So, but it doesn't seem people do that anymore. We're just going to use the regular words from now on. Is that all right? What about 7/11? What would you consider that? Yeah, it's a rational because it's not integer, right? Which means it's not whole, it's not natural. It's a rational number. So we just write rational. I'll just write it rational. I'd probably prefer you just to write out the word. All right. What about this? 2.3, but it repeats. What is it? Is it irrational? What does an irrational do? It does not repeat. Okay, this one actually does repeat. So this can be written as a fraction. Okay, it'd be 2 1/3 is what that would be. All right. So yeah, this is a rational. Okay, so both of those are rational. What about this one? We talked about that exact number actually. What is that one? It's irrational, right? The IR like negates the rational. It means the opposite of rational, right? So it's irrational. All right, that's pretty easy, right? Just learn a few definitions, learn what numbers are what. Even though I said earlier I don't really like this stuff, I still think it's relatively important because there's going to be a lot of times where definitions and theorems and things like that will talk about integers, they'll talk about whole numbers, they'll talk about irrational versus rational. And then eventually, I believe, what happened? Why did it do that? Did I touch something? All right, I think we're good. Eventually, I think in this book, not 100% sure, I know in the pre-calc book, but I'm pretty sure in this book, I think they're going to touch on imaginary numbers a little bit later on. It's probably towards the end. I have not taught out of this book. Years ago, I taught Algebra 2, like every year, a whole bunch of years. And then I came here and I taught Algebra 2 for a few years. Then the other math teacher, did I tell you the story? The other math teacher down the hallway, her daughter was going to take Algebra 2, and she wanted to teach her daughter. She says, Aaron, could I please teach the Algebra 2 class this year? Because I really want to teach my daughter. I said, well, as long as I get the class back. Well, that was like 15 years ago. And finally, after 15 years, I got the class back. But the lady that used to teach here, she's now the head of the math department at Wilmington University. So she's done good things. And now she earned her doctorate and everything. So now she's Dr. Bonsbach. So I think that's kind of cool. All right. Let's do some more. Let's talk about graphing. Everybody's favorite.
It will be held immediately after school in NCR on Thursday, September 5th.
All right. So every real number, all the numbers we've talked about are real numbers. Every real number can be represented on a graph. Even an irrational number, which is kind of weird, but even irrational numbers could be represented on the graph. I don't see how, but that's what they say. All right. So how do we do that? Well, let's do this. We don't always have to put 0 in the middle, but a lot of times we do. And then, of course, to the right, we have positive numbers. And to the left, we have negative numbers. All right, so that would be what? 1, 2, 3, 4, 5. This would be -1, -2, -3, -4, -5. I'll just stop right there. Okay? So there you go. You got a graph, you got a number line. What if they, I'll just do this because we're running out. What time did I say this goes to? 14? Okay. So what if I asked you, let's push this up a little bit, to graph the following? What if I said, I'm going to put I think they put a colon. Sometimes people put a parentheses. But point A, that capital A right there, right? You guys took geometry last year, right? You didn't take geometry?
Nope.
You've never had geometry?
Nope.
Why are you in Algebra 2?
I don't know.
Okay. Well, anyway, that's all right. You don't really need geometry to be in here. But B, we're going to graph 1.5. C is 2.3 repeating. D is negative square root of 3. And then E is -1/4. All right, so here's what we want to do. There's our graph right there. The A, B, C, D, and E represent points on this graph right here. Okay, where do I put A? Do I put A right here? Do I put A right here? Well, they kind of tell you where to put the A, don't they? At where? At where? At -3. So you go to -3. Let's change colors. You go to -3, and you put a dot right there. Now, I don't just put a dot because I don't know which one of these is that, right? So what do I put on top? Put a capital A. All right, so that's point A. So point A is at -3. That's all they're asking. Very simple, not that hard, all right? So it's not real Algebra 2 yet. It's going to be a while before you get to it, but actually not too long. What do we do here? 1.5. Where's 1.5? I don't even have 1.5 on the graph. Well, it's halfway, right? It's halfway between the 1 and the 2. So put a point right there, and then we're going to put what? Put B. And then C is 2.3 repeating. So, I mean, I can't get super accurate with this little graph right here. So 0.3 is not halfway. It's a little short of half. So I'll put it right there, and then I'll call that C. Point D is negative square root of 3. What did we say square root of 3 was? 1.7 something, right? And there's no way I can get that accurate on this graph, but it is negative. So it's negative 1.7. So I'm going to go, there's -1, there's half. I'm going to go a little bit further, about right there. That would be negative square root of 3, and that's point D. Everybody with me? Yeah, simple, easy stuff. -1/4. Well, 1/4. Well, 1/2 would be halfway, right? 1/4 would be here. So it would be about right there, -0.25, right? And this would be E. And that's all they're asking you to do. And that's one of the other examples. That's actually example 2. Example 2. Everybody good with that? Yeah, super easy. Now, sometimes I get accused by students, Mr. Hammer, you always say it's so easy, and I don't understand what you're talking about. So if I just keep saying it's easy and you don't understand it, let me know. I'll stop and help you out. 14, huh? Okay, I can get through a couple of these. I don't think I'm going to be able to get through everything, but here's something I'm almost positive that you learn, and you probably didn't like it that much, but maybe we'll figure it out here. We're going to have some different properties of addition. That's what this is called. Properties, I'll just shorten that. Properties of addition. I bet you anything you've learned these things before, okay? Commutative property. Do you remember that word? Yes? No? Okay. Commute. So if I have a car and I'm going to work, what do I say on my drive to work? I'm doing what? It's a commute. I'm commuting, right? So it's not communicate with an N. There's no N in there. Everybody hear that? Okay, that's what I thought when I first saw this word when I was a kid and learned this. It's commute, is to go back and forth. Everybody see that? Back and forth. So here's the commutative property of addition. So A plus B is the same as, now look, commute means do what? Go back and forth. So A plus B is the same exact thing as what? B plus A. All right? That's what the commutative property says. It doesn't matter what order that you do that. Now, is there a commutative property of subtraction? No, because, I don't know, like 5 minus 2, is that the same as 2 minus 5? It's not, is it? So there is no commutative property of addition or of subtraction, but there is of addition, all right? I'll do another one, and then we're going to have to leave pretty soon here. Associative property. Associate, right? You group together. If you associate with people, right, you group together, and that's what this associative property is. So watch. What if I had A plus B plus C? Watch this. Everybody watching? What if I was to add those up, like 3 plus 2 plus 1? Do you do all three of those in your head at once? I don't. I do the first two, I add it, and then I add to the third one. Don't you? Yeah. Or you could do what? You could have added what? The B and the C together, and then added it to the A, like this. Couldn't you? Yeah. Aren't they both the same? Yes. So associative property says that you could do that. You could group them differently with addition. Again, subtraction doesn't do that, but addition does. Okay? All right, I still got a couple minutes. I can get through this next little part here. Identity. What in the world is that? Identity. Your identity, your identification, who you identify as, okay? That word's being used all the time in the world now. Okay, that's a different story. But if you look in the mirror, you're looking at yourself. Agreed? So identity property basically means if you have A, and I'm going to add something to it, but I want to get exactly what I started with. What would you add to A to get A? 0. That's the identity property of addition. Okay, because you end up with what you started with. Everybody see that? This is all addition right now. Two more, sorry. Let's go inverse. When we talk about the inverse of addition, watch. If I add, what's the inverse? What's the opposite of A? It's negative A. And what do I get? I get 0. So the inverse is, what do I add to that number to get 0? I just add the negative of that number. Okay? That's easy, isn't it? Yeah, and one last one. Everybody loves this one. If you took Algebra 1, distributive property. Okay? This is super easy because you use this a ton. We even did this in geometry, didn't we? We did some of this stuff, I think. So let's take a look. If I wanted to multiply that through, what do I do with that A? Multiply it by the B, multiply it by the C. What do I get? AB plus AC, and you're good to go. So that's called the distributive property. All right, we got some more to do. We're not going to do it today because we ran out of time, but we did properties of addition. It was called the distributive property. So we did properties of addition. Tomorrow we'll finish up, and we're going to do the properties of multiplication. We'll do properties of multiplication tomorrow, okay? So no homework tonight. Oh, the bells are ringing now. That's good. All right, that's it. We'll finish this up tomorrow.